Okay, good morning. I hope this is going to work. It was not working a little earlier, but we'll see. This is the solution for the Unit 3 progress check free response. And Unit 3 is about energy and that kind of thing. This is a doozy of a question for a number of different reasons. First off, it is structured poorly in the sense that the formatting on the page is incorrect. The parts are not in the correct order. So I did send you a little notice about that. But let's have a look at the question and see what we can do with it here. So it says read the question carefully, show your work for each part of the question. The parts may not have equal weight. So there's a picture of a skier on a slope and then it goes back up. So this is reminding me of the roller coaster problem. So we start at an unknown height h1 and we go down to ground level and then we're going to get launched off here 10 meters above the ground. So it says a ski jumper starts from rest at point A at the top of the hill as of height h1 above point B at the bottom of the hill. The skier and skis have a combined mass of 80 kilograms. The skier slides down the hill and then up a ramp is launched into the air at point C that is a height of 10 meters above the ground. The skier reaches point C traveling at 42 meters per second. Calculate the height h1. Okay, so this isn't too bad at all. I think what we got here is a situation where Unit 3 FRQ, I think we have a situation where we're going to use conservation of energy to solve this problem. So for part A, we're going to use conservation of energy, and we're going to say that the potential energy that the skier has at the beginning of the problem is going to turn into, well, at part C, we are going to have some potential energy and some kinetic energy. Now, if you wanted to be more careful, you maybe want to write out U equals U plus K, but I think a grader will definitely see this. But this is H1, and this is the height at point C, and this is the velocity at point C. And the interesting thing about this, if we want to solve for H1, is that, of course, the masses will cancel out. So it doesn't really matter that the skier is 80 kilograms. So G times H1 is going to equal G times HC plus 1/2 velocity at C squared. Okay, probably a waste of ink there because we can go ahead and put numbers in. Let's divide through by G and we'll be in good shape. H1 equals H2 or HC, which is 10 meters, plus 1 over 2 times 10, that's 2 times g. Remember, we're dividing through by g, and then that is going to equal our velocity at point C, which is 42 meters per second, and that's going to be squared. Wow, that's a pretty high velocity, considering that freeway speed is 30 meters per second. This skier must be a thrill seeker of epic proportion. Okay, so H1, when we put all of this together, is going to wind up being 10 plus, and let's get the old calculator out. We're going to have 42 squared divided by 20 is 88.2. So we're going to go with a 98.2 meters. Up 100 meters or so is the answer to this question. Okay, so now let's talk about part B. And the question for part B says calculate the speed of the skier as the skier reaches point B. Okay, that's good to know. We can do that. So for point B, well, we could compare any 2 points we'd like. Let's go ahead and compare point A to point B. And because we do have a new height. Now, maybe this isn't the smartest thing to do because if I had made a mistake, I'd be using a mistaken number over here. But I'm pretty confident, and this is pretty simple. The masses cancel again. We divide through by, no, we don't divide through by g. We multiply through by 2. 2gh1 under a square root is going to be vb. That's going to be the square root of 2 times 10 times 98.2. Okay, so I've got our 98.2 in the calculator here. And we're going to multiply by 20, and that's going to give us 1964. We got to take a square root. 44.3. Okay, doing good so far. Not bad, not bad, not bad. Part C. Is the work done by the gravitational force on the skier as the skier slides from point A to point B positive or negative? And justify your answer. Okay, so we need to talk about the work done. Now, if we take a look at the situation, the positiveness and negativeness of work done has to do with the alignment between the force and the displacement. So if we take a look at the skier at any point, the force is largely down, the gravitational force, the skier's weight, and the displacement is also going to be downwards. So those are in alignment, and that means that we're going to have positive work done. The other way to argue that positive work done is to argue from the other side and to say that the energy, the change in kinetic energy, is a positive. And since work is equal to the change in kinetic energy, that's the work energy theorem, the kinetic energy of the skier increases from 0 to a positive number down at point B, so that means that we can infer that positive work is done. So either way you want to slice this, the answer to question C is positive, and the justification is either an alignment of force and displacement or looking at the sign of the kinetic energy change. Okay, so we're moving on to where it gets a little wacky here. We're going to be moving on to part D. And part D has a little wrinkle. It says the skier leaves the ramp at point C at an angle 25 degrees above the horizon. And that wasn't on the drawing before, so this is new information. And for part D, they want us to calculate the kinetic energy of the skier at the highest point in his trajectory. So, kinetic energy of the skier at the highest point in the trajectory. That is going to take some thought. But we can use a little bit of a trick that we learned about projectile motion, and that is that even though this skier is launched off of a ramp that's up high, the skier is going to travel along a parabolic trajectory and land on the ground over here. And at the highest point, the interesting thing is that the velocity is equal to just the x component of the velocity. And that's going to be the same x component at the point of launch. So if we can find what Vx equals, we can put that into the kinetic energy formula. But Vx at the point of launch is really easy, because Vx at the point of launch is just going to be the velocity at point C times the cosine of the angle. So that's going to be the number they gave us, 42 meters per second, and times the cosine of 25 degrees. And I'll get that into my calculator here. In fact, let's mark this as answer D. Put a line over here to separate this out. I'm trying to get the maximum use out of the paper here. So here we go, 42 times cosine of 25, and that gives me 38.06. So let's stick with just 38. So Vx is going to be 38 meters per second. Now that's not the answer, because they wanted the kinetic energy of the skier. So now we need to say the kinetic energy of the skier at the highest point, max altitude, is going to be 1/2 of the mass of the skier times the velocity of the skier at that point squared. So that's going to be half of 80 kilograms, or 40 kilograms, times 38 squared. So the kinetic energy is going to be, here we go, 40 times 38 squared equals 57,760. And you might worry that that's a really big number, but remember that joules are a fairly small amount of energy. So for a heavy person going at well over freeway speed, that's a reasonable amount of energy. Okay, so in the actual question at this point, we get part II, which bothered me because there was no part I under D. And it says the angle is increased to 35 with the new horizontal distance traveled by the skier. Wait, the horizontal distance traveled, we were trying to find the energy. So this is misplaced. So I figured out that it must be part of part E. Down here we have part EI, and then up here II. So what I think you need to do is to go ahead and move this part EI up into here and solve this first. So EI says calculate the horizontal distance from the point directly below C to where the skier lands. So what we're looking for here is we're looking for how far from here to here does the skier go. And that's going to require a new piece of paper, because that's a bit of a pain in the buttocks. So in order to solve that problem, and then we're going to mark this as part EI, in order to solve this problem, we need our initial launch velocity to be componentized into the two components, and there's going to be a y component and an x component. I used to use blue and green. Now we know that this one is 38 meters per second, and if we do 42 times the sine of 25, we can find the y component. So let's do that. 42 times the sine of 25. So 42 times the sine of 25 degrees equals 17.7 meters per second. Now we have our launch conditions, and we can solve this problem. The way we normally solve this problem, now look, if you had a special range formula written down, you might be tempted to use it, but watch out, because that range formula is for when you're launching from the ground and landing on the ground. This is not launching from the ground. This is launching from someplace above the ground and landing on the ground. So it's best just to go ahead and solve this. We're going to use the y information to get our time, and then we're going to use that with the x information to find out how far it goes. So the y Swiss Army equation says that y final equals y initial plus v initial y times t plus 1/2 of the y acceleration times t squared. Now the y final is going to be 0, but the y initial is 10. We're launching from 10. That's going to be 17.7 times t, and this is going to be minus 1/2 of the acceleration due to gravity, so minus 5 times t squared. So we have ourselves a quadratic where a is equal to minus 5, b is equal to positive 17.7, and c is equal to 10. So we can put that into the quadratic equation. Now, the green pen here is a little smashed, so I'm going to go ahead and do this. So it's minus b, so minus 17.7, plus or minus the square root of 17.7 squared, minus 4 times a, which is 5, but that's a minus 5, so that becomes a plus, times c, which is 10. And then it's all over 2 times a, or minus 10. Okay, that's important that this is minus on the bottom, that's a minus here. We need these, the top and bottom, the numerator and denominator, to be both negative, because we're looking for a time, and times are going to be positive. First thing you usually do is look at this discriminant to see if everything's going to be okay. It's a positive number plus another positive number. That's going to be okay. Let's just go ahead and figure out what that discriminant is going to be. 17.7 squared plus parentheses, well, 4 times 5 is 20 times 10 is 200, so I'll just put 200 in there. And that gives me 513.29, and when we take the square root of that, we get 22.66. So this is going to be minus 17.7 plus or minus 22.66 all over minus 10. Now remember, we need this to be a negative number, so if you were to add positive 22.66 to negative 17.7, the numerator would become positive, and the answer would become negative and not make any sense. So you have to use the lower sign. You have to subtract. So let's do that. 17.7 plus 22.66 is 40.36, and that's a negative 40.36 over negative 10. Looks like this is going to be 4.04. Let me write that. Time equals 4.04 seconds, or something right around 4 seconds. Okay, we used 10 for G, so we're not exactly correct. So this is going to be about 4 seconds, and from that we can find the x, the horizontal distance, which is VIX times this time, which is 38 times 4.04, or whatever 38 times 4 is. Looks like it's going to be 152 meters. So this is the answer for part EI. Now we can look up and say part II. Part II says, if the angles increase to 35 degrees, will the new horizontal distance traveled by the skier be greater than, less than, or equal to the answer? Okay, II. So this is an interesting thing. We know that if you're launched from the ground to the ground, that 45 degrees gives you the maximum range. That lower angles actually land earlier because they're not in the air very long, because they don't have as much y component. And steeper angles actually land earlier as well, because although they are in the air for a long time, they don't have as much horizontal component. So it turns out that a 45-degree angle is the steepest, and that complementary angles equal amounts on either side. So a 35-degree angle would be the same as a 55-degree angle. But that's for being launched from the ground. When you're being launched from a high place, this is not exactly true. It's largely true, and so you could probably, and the AP graders said that you could allude to this and say, well, at 35 degrees, you're higher up than 25. So you will probably go a little further because you're closer to this ideal 45. But I'd say that that's a little disingenuous. Why don't we look at our process here and say that if we had made some changes, if we had gone to 35 degrees, this would be a bigger number and this would be a smaller number. And let's see what would happen. Well, over here, if the 17.7 is a bigger number, then the bigger number squared is going to give me a much larger discriminant. So this would be a bigger number. This would also be a bigger negative number. And maybe we're going to say that it's just about a wash because we're going to be, oh, no, because we're subtracting. So this is definitely going to be a much bigger number. So the time is going to be a bigger number. And the time is a bigger number by, I think, a larger factor than this is going to decrease. So I think we could argue that the increase in time from this process is a bigger effect than the decrease in the horizontal speed. That's probably what I would do. But either way, this is only worth 1, maybe 2 points. So a good guess is that it would go farther, or what is they say greater than. And because, and then right in here you have to dance. You have to make some sort of coherent explanation. I would go look back and look at this process. You might want to look at this fact. I think they stepped in it. I think this is a kind of a bad question because it really can't be done analytically. And if you do it analytically, it takes a long time. Once again, remember, pick your battles, bro. If something's going to take a long time and it's only worth 2 points, it's best to move on because there is still another part of this. Yep, there's a part F. And part F has a wrinkle. It says, after landing, the skier slides along horizontal ground before coming to a stop. The skier's initial speed on the ground is the horizontal component of the skier's velocity when the skier left the ramp. Okay, so that's back. And by the way, I think we have to assume here that we are back to a 25-degree angle. This is also ambiguous. Are we talking about the 35-degree angle you were just talking about, or are we back to the 25? So this is a bit odd. I know there's an argument that says that this is if the angle, so I says, it says it's 25-degree angle, so, we stick with that. Yeah, sure, you're right. But it is a little bit ambiguous. The horizontal component of the skier's velocity when the skier left the ramp. The average coefficient of friction is given as a function of distance moved by the equation mu equals 0.20x. And this is weird because mu is not a constant. And we've always treated mu as if it was a constant. So typically, if you were going to solve this, and this is part F, you would probably do something like say, okay, well, there's a force of friction. The force of friction is mu times the normal, which is mu times m times g, because this is on horizontal ground. And from that force, I can get an acceleration. And from that acceleration, I can find the distance slid. But to do that, you would use the equations of motion. And the equations of motion assume that the acceleration is constant. But see here, we have a fact that this is going to be 0.2x times m times g. That means that the acceleration isn't a constant, it is a function of x. And this screams out for calculus. Whenever something is changing throughout the problem and you're trying to solve something, this screams out for calculus. Now, at first I was thinking, oh my God, a differential equation. Not so fast. The work done is equal to the change in kinetic energy. We're going to bring this thing to a stop. So the kinetic energy this thing has to start with is going to be equal to the work done, which is the integral of the force over the distance and going from 0 to x. This is going to be a great way to do it. So what we have here is 1/2 m vx squared. Remember, it lands and has the horizontal velocity that it had throughout the process here. Horizontal velocity doesn't change. Is going to equal, and now we're going to integrate between 0 and the final resting point. We're going to integrate the force, which is 0.2x times m times g. And that's going to be over dx is our integration variable. All right, that's not bad. We have a 0.2, we have a half, we have some m's that cancel. That's sweet. We have known values here, so let's just get all the known stuff to the other side. So what we're going to have is 1 over 2 times 0.2, which is 0.4. This comes over as and then g on the bottom here, which is 10. And then we're going to have a vx on the top, so let me cross that out, and that's going to be squared. And all of that is going to be equal to the integral from 0 to x of x dx, which is, of course, x squared over 2, evaluated between 0 and x. Okay, over here we have our 38 squared over 4 times 10, which is 4. Okay, that's good. And over here, we have, we have x squared. Okay, so we need to get this 2 over to this side, so we put a 2 up here. There we go. This is getting to be a little kludgy. Okay, so what is that? That is 38 squared over 2 is going to equal x squared. When you put x in for here, and then you put 0 in from there, you get these limits. So that means that x is going to be the square root of 38 squared divided by 2, or it's going to be 38 divided by root 2, which is going to be 38. Oh, my calculator turned off. Click, 38 divided by parentheses square root 2 in parentheses, or 26.9 meters. So we're going to skid along the ground about 26.9 meters, which is the correct answer. So that is how to tackle this problem. This is probably the most difficult of the free response questions that I'm going to give you. And look at how much work I had to do here to solve this thing. You know, we got through part A and B and even C pretty handily. Part D, where they started folding in projectile motion, but they did so by asking about energy at first. So this is still valid and this is good. But then we just got ourselves back to Unit 1. So I'm a little confused as to why, except that the AP test just loves to mix and match things. But Part E is all Unit 1 stuff. And then we go back to energy and the work energy theorem to solve Part F. So there we go. I know this one's a little long, but this problem was rather egregious. I will look for scoring point breakdown and try to get that to you in the near future. All right, I'm going to get this thing uploading as quickly as I can because we've already lost a bit of time. It is 10 in the morning, so this should be up by about 11:30, and you should have it before noon. See you on the other side.